Today I will start with session number 5. This is having the topics in model number 4, that is stability of the control system. Okay, so now in this session I would like to start with nominal stability using frequency response. So this nominal stability using frequency response, it is a classical and lasting tool which can be used to assess the stability of a feedback loop is called as Nyquist stability theory. A nominal stability using a frequency response, it is a classical and lasting tool which can be used to assess the stability of a feedback loop is Nyquist stability theory. In this approach, stability of closed loop is predicted or calculated using the open loop frequency response of the system. In nominal stability using frequency response, you are going to calculate the stability of the closed loop using open loop frequency response of the system. This can be achieved by plotting a polar diagram of the product of G of S into C of S. It is achieved by plotting a polar diagram of the product of G of S to C of S and then counting the number of encirclements of the -1 to 0 point. We show this how it works. So for example, I'll take one problem. Draw the root locus of the feedback system whose open loop transfer function is given by G of S H of S is equal to K divided by S into S plus 1. So in first step, so you have to determine the number of open loop poles and zeros. So in the equation, as I told, and this given equation or transfer function, it consisting of denominator and numerator. The denominator means denominator it is having any s terms, that is called as zeros. If you are in the numerator, if you are having any s terms, that is called zeros. In denominator you are having s terms, those are called poles. Now in the numerator you are not having any s term, so in denominator you are having s is equal to 0 1 pole, s is equal to -1 1 pole. So number of open poles n is equal to 2, number of zeros is m is equal to 0. So now open loops are s is equal to 1, s is equal to 0 is one loop, s is equal to -1 is one loop. Next you have to mark these open loops as in the these poles in the s plane. So this is real axis, this is imaginary axis. S is equal to 0, you have to mark with n2 sign as a pole at 0 or center, and -1 it is on the real sigma axis or real negative real axis, that is shown by into mark with -1. So these poles are marked on the S plane. Now in the next step you have to go draw asymptotes. No. Next step 3, determine parts of the root locus on the real axis. So here you have to find out the test points on the positive real axis. You see this is S test point. Vectors from S is equal to 0 and -1. Theta 1 is equal to 0, theta 2 is equal to 0. Here test points in between the open loop poles are, this is a test point. Okay, so here vector theta 1 is equal to 180 degree where S is equal to 0 from pole, and another pole will be at -1. Here also theta 2 is equal to degree, vector S is equal to -1. The in between this point is called as test point. Now vectors from S is equal to 0 and second one is S is equal to -1. Theta 1 is equal to 180 degree and theta 2 is equal to 180 degree. So here from 0 to S, this is the test point. When theta 1 and theta 2 are 180 degree, this is test point when S is equal to theta 1, theta 2 is equal to theta 1 is equal to 0 and theta 2 is equal to 180 degree. Now you have to determine breakaway and break-in points in the next step. So to find out the breakaway and break-in point, characteristic equation from the given transfer function you have to form. So k is equal to minus s into s plus 1. So it will give s square minus s. So therefore if you differentiate with respect to s, dk by ds is equal to minus 2s plus 1 is equal to 0. So breakaway point will be represented as sigma is equal to minus 0.5. And gain at the breakaway point kb is equal to minus 0.5 minus 0. Minus 0.5 is what? And minus 0.5 minus of minus 1, that is equal to 0.25. So this is your breakaway point. So one root locus of the branch, one branch of the root locus will coming from 0 pole, another branch will be coming from minus 1. So here this is at a point minus 0.5 on negative real axis, that is a breakaway point. Now you have to draw the asymptotes of the root locus. So angle of asymptotes theta c is equal to 180 degree plus k into 360 divided by n minus 1. 180 degree plus r minus 360 into k divided by n minus 1 is 2. So if you put k, because n minus 1 is equal to 2, you have to put k is equal to 0 and 1. So therefore you put k is equal to 0, in this equation you will be getting the theta is equal to 90 degree, which is one asymptote. And if you put in this above equation k is equal to 1, you will be getting another asymptote 270 degree. So centroid of asymptote is P1 plus P2 up to Pn minus Z1 plus Z2 up to Zm. So this is real parts of poles, this is real parts of zeros. So 0 minus 1 divided by 2. So is equal to minus 0.5. Again it will be the same at point centroid. Okay, this is one asymptote at theta is equal to 90 degree. This is another one is theta is equal to 170 degree. So now 6 and 7, in the step 6 and 7 there are no complex open loop poles or zeros. So therefore angle of departure and arrival need not to be calculated. So in the next step of 8, you have to find out, determine the points on the root locus crossing the imaginary axis. Okay, so to find out the points on the crossing of imaginary axis is, so 1 plus g of s into h of s is equal to 1 plus g of s is your transfer given function k divided by s into s plus 1. H of s is unity feedback, so is equal to 1, so need not to write here. So you simplify this, you will be getting s square plus s plus k is equal to 0. So otherwise you put here b of j omega is equal to, you in this equation you substitute s is equal to j omega, it will become j omega square plus j omega plus k. So k minus omega square plus j omega. So k minus omega square is equal to 0. So j omega is equal to 0. That means you are not having any poles are not, or any root locus will not crosses the imaginary axis. So the root locus does not cross the imaginary axis for any value of k is equal to infinity. So now this is the your root locus diagram. So this is how, what are the given points you have derived. This is test point S, and this is 180 minus theta, this is one angle. This angle at point minus 5, this is at the centroid you are having 90 degree. This angle is theta, theta 2 is equal to 1 minus theta. So like that you are going to calculate. Now here you are going to s is equal to minus 1 plus or minus root of 1 minus 4k divided by 2. So this is how root locus of the given transfer function is g of s h of s is equal to k divided by s into s plus 1. This is your k is equal to 1 by 4. this is k is equal to 0, that is -1. This is k is equal to 0. At k is equal to infinity, this is one asymptote. At k is equal to infinity, this is another asymptote, because it is not your root locus will not be crossing this imaginary axis, though this is like straight line. So I hope this will end of this session. Now I will stop this session. Thank you for watching this video.